Alright, for 1A, we're going to start by sketching a triangle to see what information we have. So if I sketch this triangle, call it A, B, C, I know the angle A is 76, side A is 18, side B is 20. And when I look at this, it tells me that I am given a triangle with side-side angle, which means I'm going to use the law of sines, and I need to be concerned about the ambiguous case. So I have to check for multiple possible triangles. So to set this up, I'm going to solve for missing angle. I'm going to start with angle B. So that's going to be the sine of B over 20 is equal to the sine of 76 degrees over 18. So I get the sine of B equals 20 times the sine of 76 degrees over 18, and that gives me 1.078. So that right now means I'm done and I have no possible triangles because sine of any angle must be between -1 and 1. For 1B, I'm going to start the same way. I'm going to sketch a triangle, A, B, C. This is 33 degrees, 6, 10. And I'm going to do the exact same thing I did on the previous one. I'm going to start finding angle B. So the sine of B over 10 is equal to the sine of 33 degrees over 6. So B is going to be the inverse sine of 10 times the sine of 33 degrees over 6, which gives me 65.2 degrees. So that means I have at least one triangle. So I'm going to call that B1, and then we check for a second possible B, B2, with 180 minus B1, which is going to be 114.8 when I subtract those two values. So looking at this, 114.8 plus the 33 that I was given is still less than 180, so I do have two possible triangles. So I'm going to go ahead and I'm going to finish solving for triangle number 1. So I have two angles now and two sides, so I need the missing angle, angle 1, and I need side A1 as well. So angle A1 is going to be 180 minus the sum of 33 plus 65.2, and that gives me 81.8. And then side A1 is going to be found using the law of sines. So I have A1 over the sine of 81.8 degrees over, I'm going to use side C over the sine of angle C, and side A1 is going to be 10.9. So there's my complete first triangle. And then my second triangle, now I'm going to use this for B, 114.8, and I'm going to follow the same steps. So angle A1, or angle A2, should say, is 180 minus the sum of 33 plus 114.8. So A2 is going to be 32.2 degrees. There's my second angle, and then my last side, A2, is the sine of 32.2 degrees over is equal to 6 over the sine of 33 degrees. So A2 is going to be 5.9. Now I have two complete triangles, and that problem is finished. Alright, number 2, same idea. I'm going to start by sketching to see what we have. Hopefully everyone sees right away that I'm given three sides, so we're going to have to use a law of cosines. There's side, side, side is the law of cosines, and that said, So we're going to use, we have to find one of the angles. We have to find two of the angles, then 180 minus those two to find the third one. Doesn't really matter which one we start with. I'm going to start with angle A, and we're going to use the alternate form. So the cosine of A is equal to B squared plus C squared minus A squared over 2 times B times C. So A is going to be equal to the inverse cosine of all that. And I would recommend just plugging that all in the calculator as is, and we're going to get 20 degrees. So there's my first angle. My next angle is going to be angle B. And we said in class, even though we could switch to law of sines here, since we started with law of cosines, we should probably stay that way just to make sure we don't have any issues. So again, the alternate form, cosine B is equal to, this time it's going to be 72 squared plus 45 squared minus 30 squared over 2 times 72 times 45. And when we take the inverse cosine of all that, we get the angle B is 13.2 degrees. So then angle C is going to be 180 minus the 20 plus the 13.2. So angle C is 146.8 degrees. Alright, 2B, once again, I've got a triangle labeled A, B, and C. Got 1.42, 0.75, and 1.25. Again, I've got three sides, so we're going to find the three missing angles using law of cosines. So I'm going to start with angle A. So alternate form, cosine of A is equal to 1.25 squared plus 0.75 squared minus 1.42 squared all over 2 times 1.25 times 0.75. And if we take the inverse cosine of all that, get 86.7 degrees. So there's angle A. Angle B, cosine of B is equal to 1.42 squared plus 1.25 squared minus 0.75 squared all over 2 times 1.42 times 1.25. Inverse cosine of all that leaves me with 52.6 degrees. And finally, angle C is 180 minus the sum of angle A plus angle B. So angle C is going to give us 40.7 degrees. 3A tells you we have 2 points on opposite sides of the Grand Canyon. Point C is 200 yards from A. It gives us the measures of angles B and C, and wants to know the distance between A and B. So again, we should start by sketching a picture. Obviously not to scale. Something maybe like that. So there's my picture. I know that the distance from A to C is 200 yards. I know that the angle at B is 87 degrees and the angle at C is 67. So when I look at this, I've got angle, angle, side. So since we have angle, angle, side, we can use the law of sines. Since we have an angle, side, opposite pair, we can use the law of sines to find side AB. So AB over the sine of 67 degrees is equal to 200 over the sine of 87 degrees. So AB is going to be 200 over the sine 87 times sine 67, which is 184.4 yards. 3B, so we've got two observers standing on a shoreline half mile apart. So here's A, there's B, half a mile. And they measure the angle to a sailboat, out here angle C. And we're told the angle A is 63 degrees, angle B is 56 degrees, and find the distance from each observer to the sailboat. So that's going to be the distance from A to C and the distance from B to C. Well, when I look at this, I can find my third angle. Angle C is going to be 180 minus 63 plus 56, which is 61. And now I can use law of sines again twice. I can use it once to find AC. I can use it another time to find BC. So for AC, which I called x, we're going to have x over the sine of 56 is equal to 1/2 over the sine of 61. So x is going to be equal to 0.47 miles. So the distance from A to C is 0.47 miles. And then we can do the same thing to find y. Y over the sine of 63 degrees is equal to 1/2 over the sine of 61 degrees. So y equals 0.51. So that means that B to C is 0.51 miles. All right, 4A. So we're given two magnitudes and angle between them. It wants us to draw a picture that represents that information and find the magnitude of U minus V. So let's start with the picture. So if we know that the angle between two vectors is 25 degrees, that means that if I have vector U and then I have another vector V, then this angle here is 25 degrees. Notice I connected the two tails together. That's how we show the angle between them. It says draw a picture that represents, so one other thing. So we have the magnitude. So V is 22 and U is 33. So we know all that. Draw a picture that represents the given to find the magnitude of U minus V. So we discussed in class that for U plus V, we would connect the vectors tip to tail. So I would take like U and connect V to that. So then this vector along that line would be U plus V. Well, if I want to subtract the two vectors, V needs to be going in the opposite direction because U minus V is the same as saying U plus negative V. So we need to flip V around. So what that does, instead of connecting them tip to tail, we generally connect them tail to tail, just like we drew our original picture. So we have a triangle that looks like this: U, which was 33, V, which was 22, this angle was 25, and then that guy right there is U minus V. So now that we have that, we can find the magnitude of that missing side by using the law of cosines, because we have two angles. We have two sides in the included angle. So the magnitude of U minus V is equal to the square root, because remember it's the log cosines, it's the side squared, so I'm just taking the square root of, if we call that a, it's b squared plus c squared minus 2 times b times c times the cosine of the included angle. So the magnitude of u minus v is equal to, it's going to be 16.0 something. We'll just call it 16. So that means that that side right there is 16. Alright, and then for part B, I'm going to resketch that same triangle that we just had. So u minus v. So there's u, which is 22. Oh, sorry, u was 33. V was 22. There's u minus v, which we just found out was 16. And we know this angle is 25. And it's asking us now to find the angle that the resultant makes with u. So that's going to be this angle right here. So I'm going to go ahead and use law of sines this time. We'll call this theta. So we've got the sine of theta over 22 is equal to the sine of 25 over 16. So theta is going to be equal to the inverse sine of 22 times sine 25 over 16. And we get an angle of 35.4 degrees. Alright, 4C, very similar to part A, except this time it wants us to find the magnitude of u plus v after we find a vector. So going back to what we did for part A, we had a vector u and then a vector v, and when we connected them tail to tail, that vertical piece ended up being u minus v because they were connected tail to tail. Well, when we do tip to tail, which is how we do it for adding vectors, we get a vector u plus a vector v, so we connect that to the end of the previous vector. And then we get this triangle here, and that long red piece is now u plus v. So that's the big difference between adding and subtracting them. The other thing that's going to change is this angle is no longer that 25 that it used to be. If we extend that purple line u out, we can see where this little green angle that I just marked matches the angle from the u minus. So that's a 25 outside, which means it's got to be 155 inside the triangle, because those are supplements of each other. So since we know that now, we can find the magnitude of u plus v, which is going to be that same formula using law of cosines, the square root of, we still knew this was 22, this was 33, so we've got 33 squared plus 22 squared minus 2 times 33 times 22 times the cosine of 155. So the magnitude of u plus v is equal to about 53.7. If we use a calculator, we actually get 74975. So we'll call it that. Okay. Now part D, the last part, find the angle that resultant makes with u plus v. So we have, I'm going to redraw that triangle. So here's u, here's v, here's u plus v. So we knew that was 53.75. We knew this side was 22. This is 155 degrees. This is 33. And now we're looking for this angle theta. So we can use law of sines or law of cosines here. It doesn't matter because we have enough information for either one. I'm going to use the law of sines. So the sine of theta over 22 is equal to the sine of 155 over 53.75. So theta is going to be the inverse sine of 22 times the sine of 155 over 53.75. So theta gives me 9.96, which I'm going to round up to 10 degrees. All right, for 5a and b, we're finding the magnitude and direction of the given vector, whether we are in component form or linear combination like we are here. We're going to use the formula for magnitude, the square root of a squared plus b squared. Remember, a is the x component, b is the y component, and then the angle is the inverse tangent of b over a. So for 5a, the magnitude of v is equal to the square root of -1 squared plus 7 squared, which is radical 50, which is going to be 5 radical 2. And the angle is the inverse tangent of 7 over -1, which the calculator says is -81.7 degrees, but that can't be right because -81.7 is in quadrant 4, and this vector, based on the two components, left 1 up 7, is somewhere in quadrant 2. So what that means is the calculator just gave us the reference angle, 81.7. So the actual angle that we're looking for is 180 minus 81.7, which is 98.3 degrees. Similar process for b. The magnitude of the vector is the square root of 9 plus 25, which is radical 34. And then the direction, theta, equals the inverse tangent of -5 over 3. And that's going to be, again, it gives me the reference angle, -59 degrees. Now this one technically is correct because that vector over 3 down 5 is in quadrant 4, and -59 degrees would be the correct angle. So we could leave it as -59, or you can write it as 360 minus 59, which is going to be 301. Either one of those would be acceptable. All right, 6, find the component form magnitude of a vector with initial point P and terminal point Q. So we're finding vector PQ, which is the terminal, remember it's always terminal minus initial. So if I'm making vector PQ in component form, it's going to be 3 minus -5, which is 8, and 6 minus 2, which is 4. That's my vector. And then the magnitude of PQ, just like we did on the previous problem, is 8 squared plus 4 squared, which is the square root of 64 plus 16, which is radical 80, which, let's see what goes into 80. That's going to reduce to 4 rad 5. 6b, same idea. Find the vector PQ. So PQ in component form. So that's going to be terminal point -1 minus initial point 4, that's -5. And for the y components, 5 take away -7 is 12. There's my component form, and the magnitude of that is the square root of 25 plus 144, which is radical 169, which is a magnitude of 13. 7a, given those two vectors, find 2v minus u. So we're going to start with finding 2v. So we're just going to take vector v, multiply everything by 2, so we get -6, -4, and then for 2v minus u, we have that right there, which turns into -6 minus -2 is -4. -4 minus 1 is -5. For b, given those two vectors, find 2u plus v. So once again, we're going to start with finding 2u. So it's going to be -4, 10, and then -4, 10 plus 7, -12 is going to give me 3, -2. For 8, find the projection of u onto v, given the following information. Before we start, remember that the projection of u onto v is a scalar multiplied by vector v, and that scalar is the dot product divided by the magnitude squared. Remember, we talked about in class that the magnitude squared of v means we really just have the magnitude of v without the radical. So let's start by finding for a the dot product of u and v. Dot product, we just multiply the components, add them together, so I get 5. For this first one, I'll show you what we're doing. -5 times -1 plus -1 times 1, which is 5 plus -1, which is 4. The magnitude of v squared is just -1 squared plus 1 squared, which is 2. So the projection of u onto v is 4/2 times v itself. So it's 2 times magnitude, which is -2, 2. That is the projection of u onto v. Same thing for b. Find the dot product. It's going to be 3 times 6 is 18 plus -10. It's a dot product of 8. Magnitude of v squared is 36 plus 4, which is 40. So you get the projection once again of 8/40 times 6, 2, which is 1/5 times vector v, which leaves me with 6/5, 2/5. 9a and b ask us to find the exact value of the vector in component form with the given direction. So to do that, we're going to use the component form that uses the magnitude of a vector. I should probably use u since these two problems use u. So it's the magnitude of the vector times the cosine of the angle, and the magnitude of the vector times the sine of the angle. We're going to use that. So once again, it's just kind of plug and chug. We need to find the magnitude of u first, which is the square root of 4 plus 36, which is radical 40, which is 2 rad 10. So then component form is going to be 2 rad 10 times the cosine of 150 and 2 rad 10 times the sine of 150. And we need to simplify that. We need to find the sine and cosine of 150. Those are on the unit circle, so we need the exact values. 150 is in quadrant 2, so cosine should be negative 2 rad 10 times negative rad 3 over 2, and 2 rad 10 times 1/2. So I get negative rad 30 and rad 10. That is the component form of vector u in the direction of angle 150, or some other vector in the direction of 150 degrees. All right, b, same thing. I'm going to find the magnitude of u. Square root of 25 plus 4, which is radical 29. So component form, rad 29, cosine 210, rad 29, sine of 210. Once again, those are on the unit circle. Probably knew that because it was going to say exact value. Cosine of 210 is negative rad 3 over 2. Sine of 210 is negative 1/2. So again, if we plug them in, I have rad 29 times negative rad 3 over 2, and rad 29 times negative 1/2. So everything's negative. And that gives me a vector of negative rad 87 over 2 and negative rad 29 over 2. Alright, 10 is very similar to 9. The only difference is we're given a magnitude, but we are not given a direction, but we're still, we're told our vector needs to be in the direction of u. So the first thing we're going to do is find the direction of u. So remember, we can find the direction with the inverse tangent of b over a, and then our component form is going to be the same thing, magnitude of the vector cosine theta, magnitude of the vector sine theta. So theta, just going to put a little subscript u there so we know what we're looking for, is the inverse tangent of 6/5. That is not going to be on the unit circle. I'm going to get an exact value. Radians or degrees will work here. I prefer degrees, personal preference, whatever you want to do. So we know the degree, we know the magnitude, so our component form is just 8 cosine 50.3 degrees and 8 sine of 50.3 degrees. And our final result, when we plug this into the calculator, we're going to get 5.12 and 6.15. That's my component form of my new vector. Same thing for b. I need to find the direction of u, so it's the inverse tangent of negative 4 over 4. That is the inverse tangent of negative 1, which is on the unit circle, which is 315 degrees. And then my component form is 3 cosine 315 and 3 sine of 315. I know this problem does not say to use exact values, but we still should. Sine and cosine of 315, since that's a 45, it's going to be rad 2 over 2, negative rad 2 over 2, since we're in quadrant 4. So we have 3 rad 2 over 2 and negative 3 rad 2 over 2. Remember, always use exact values if available. 11, find the dot product and angle between the vectors. So dot product we already talked about. Angle between, remember we use the formula cosine theta is equal to the dot product over the product of the magnitudes. So for A, we're going to find the dot product, which is going to be negative 3 plus 2, which is negative 1. Magnitude of each vector we've got the square root of 1 plus 4, so that's rad 5, and the square root of 9 plus 1, which is rad 10. So cosine of our angle is equal to negative 1 over rad 5 times rad 10. So the angle itself is the inverse cosine of negative 1 over rad 50. Which means the angle is 98.1 degrees. All right. Part B, same thing. Dot product is going to be negative 8 plus 0. Magnitude of u is radical 16 plus 16, which is 4 rad 2. And magnitude of v is 4 plus 0, which is 2. So cosine of our angle is negative 8 over 4 rad 2 times 2. So the angle, when we plug that in, is the inverse cosine of negative 8 over 8 rad 2. I didn't even have to simplify it that far, but I didn't want to. But I get 135 degrees. And again, I didn't mention at the beginning, but the angle could be in either radians or degrees. It's not that big of a deal. I prefer, again, degrees, easier to work with. All right, for 12, we're given two complex numbers, and we're asked to find the quotient in trig form. So the quotient, z1 over z2, is equal to r1 over r2 times cosine of theta 1 minus theta 2 plus I sine theta 1 minus theta 2. And we relate these back to r. The r's are like the magnitudes of our complex numbers, and the thetas are the directions. We know how to find the magnitude and the direction. We just treat the real and the imaginary component like they're the a and the b. So let's start with z1. So z1, it has an r of the square root of 16 plus 48. The 48 comes from 4 rad 3 squared. So that leaves me with radical 64, which is just 8. And then theta 1 is equal to the inverse tangent of negative 4 rad 3 over 4, which if I use the calculator, I'm going to get 300 degrees. I'm going to do the same thing for z2. So I have an r2 of 1, the square root of 1 plus 1, which is radical 2. And theta 2 is equal to the inverse tangent of negative 1 over negative 1, which is going to be 225. So again, be careful. I didn't explain it here, but for both of those, the calculator is going to give us a reference angle. We need to make sure we're in the correct quadrant to get the correct angle. So now we can plug everything in. So z1 over z2 is equal to r1 over r2 times the cosine of theta 1 minus theta 2 plus I times the sine of theta 1 minus theta 2. So the quotient z1 over z2 is equal to, it's going to be 4 rad 2. It's 8 rad 2 over 2, which reduces down to that, times the cosine of 300 minus 225, which is 75 degrees, plus I sine 75 degrees. And once again, you could write those 75s as radians if you really wanted to, but that's going to be our final answer for A. All right, and finally, on to part B, last problem. So this time, same idea, but this time it wants the product of the two complex numbers. And the product, z1 times z2, is very similar to the quotient, except for we're going to multiply our distances, r1 and r2. And we're going to multiply that times the cosine of the sum of our angles. So cosine of theta 1 plus theta 2 plus I sine theta 1 plus theta 2. So just like we did on the previous one, find all my relevant information for z1. So z1 is going to have r1, which is the square root of 3 squared, which is 9, plus another 9. So this can be 3 rad 2. And theta, once again, is the inverse tangent of b over a, which the calculator, we need to make sure we're in the correct quadrant. And we get 315. And then z2 is r2 equal to 49 plus 49 times 3 when we square 7 rad 3, which is 147, which gives me the square root of 196, which is 14. And then that theta is the inverse tangent of 7 rad 3 over negative 7. Make sure we're in the correct quadrant when we get our answer from the calculator, and we get 120 degrees. Alright, so we have all of our info. Plug everything in. z1, z2 equals r1, which is 3 rad 2 times r2, times the cosine of theta 1 plus theta 2 plus I sine theta 1 plus theta 2. So our final answer for the product of the two complex numbers is 14 times 3, which is 42 rad 2, times the cosine of 435 degrees plus I sine 435 degrees. And one more time, that could be in radians or degrees, does not matter.